Okay, so here's a few questions we just need to go over for the supplemental questions for exam one. So the first thing we're going to kind of look at is a thing called law of sines, and it's a very basic ratio formula that we have right here. And it will work for any triangle. It does not have to be a right triangle. And it basically is just stating that the ratio of any side divided by sine of the angle across from it would be equivalent to any other side with the angle across from it, like side B with sine of angle B and so on. And you can flip it around and have the sine be on top and have the side length be on bottom. Just you have to be consistent. So if you're going to put sine on top, the sine needs to be on top for all the ratios. Okay, so hopefully that's familiar from your trigonometry class. And so this question right here is going to involve that formula. So right here it says the height of a balloon. A balloonist is directly above a straight road 1.5 miles long that joins two villages. She finds that the town closer to her is at an angle of depression of 35 degrees. So that's this angle right here that we're looking at. And that the further town is at an angle of depression of 31 degrees. Oops. Sorry, my pen's going a little crazy. There we go. And so, how high above the ground is the balloon? So, we're looking for the height of this. Okay, so there we go. There's our height, our unknown height. So, we need to figure this out. Well, I do have right triangles here, but in order to use my trig ratios for like sine, cosine, and tangent, you have to know at least one angle and one side in order to use those. And so the problem here is I do know some angles actually. So these two lines right here are parallel that go across here in the road. And so I have a transversal that's cutting through right here. And so alternate interior angles are congruent. So that means that this angle right here is also 35 degrees. And then same thing here, I've got a transversal here going through. So this angle of depression, which is 31 degrees here inside the triangle, that's going to be 31 degrees. Now, as I was saying, with this right here, I still can't figure out the height because I know this angle, and sure, I could figure out the angle up here, but that's still not going to help me. This angle right here. Um, and I know that the street's 1.5 miles, but I don't know this specific part just right here. That's just that portion of the triangle, and I don't know the hypotenuse. But with the law of sines, I do have two pieces of that information. If you look at the big triangle here, and so I'm going to go ahead and draw that out again. So the big triangle is right here, just a generic little sketch of it. And so remember, we're trying to figure out the height. But what I do know is that this is 35, and I know that this is 31. And so I can figure out the one up here at the top because all triangles, the angles are going to add up to 180. So I can subtract off 35 and 31. And that will leave me with 114 degrees. And so that's what we're going to have up here. Okay, so with that information, then I know that opposite of the 114, we're looking at 1.5 miles. So what I can do now is I can figure out the other two sides. We'll call this one side A and side B. I don't really need both of them. I just need one of them so that I can use my trig ratios to figure out the height, how high above the ground the balloon is. So I'm going to go ahead and do that now. So let's see, we're going to do, it doesn't matter which formula I use. I'm going to go ahead and do the one with the side on top. So I'm going to do 1.5 divided by sine of the angle across from that, which would be 114. And that ratio would be equivalent to, we'll work with A over here, A, and then that'll be divided by the sine of the angle across from that, which would be 31. So sine of 31. And so now what we'll do is we're going to cross multiply or well, actually, no, I don't even need to cross multiply. What we'll do here is I'm just going to multiply both sides by sine of 31. So multiply by sine of 31 here and sine of 31 here. And so what that'll do for me is that will cancel with that, and I will be able to figure out the A value. And then once I have that, I should be able to figure out the height of the triangle in just a second. So let's see, A equals 1.5 times sine of 31 divided by sine of 114. And let me grab my calculator real quick. So here's my calculator. One thing you will want to check is make sure that you're on degrees, which I'm on degrees. If your calculator's on radians, and you have to be careful, even if you're using a cell phone, you will need to check and figure out what you're in. Radians or degrees. We're dealing with degrees, so I'm good. So let's see. We're going to have 1.5 times sine of 31. Close that parentheses, and then I'm going to divide that by sine of 114. And so I get about we can run that to 0.846. Oops. Sorry, this pen is not working the best. Let's see. Oh well, 0.846. There we go. Okay, so now I know what side A is, which up here in my original picture, that's up here, right here. So 0.846. And so now with that information, I can figure out the height because I'm just going to focus now in on this part of the triangle right here that I'm going to put in red right there. And so I'm going to use sine of an angle. If you have sine of an angle, we'll call it theta. The ratio that should come back is the opposite over hypotenuse. And so in our example, we're going to do sine of 35 degrees, which would be equal to opposite, which in this case is the height of the balloon, which I'll just call h, divided by my hypotenuse length, which we found out was 0.846. Okay, so then to solve this, we'll multiply both sides by 0.846. So 0.846. Oops, a little too close there. 0.846. And so once again, my calculator will do the work for me on this part, and I will know the height. So let's see. I can actually take that perfect answer right there if I want to. I can round it if I want, but I've got the perfect value right there, 0.845669, so on. So anyways, I'm just going to go ahead and say multiply my answer by sine of 35. And so I get about, we'll go 3 decimal places, 0.485. 0.485, and then that's going to be miles. So that's how high up the balloon is right there. So that's our first example that I kind of wanted to review with you guys that was not covered in the text. And then the last couple I want to look at are identities. And I know these probably are not your favorite, and I understand that, but we definitely should go ahead and get some practice with this. And so the way identities work, and these are kind of the harder ones, but I think as long as you can kind of follow along with me, you're going to see it's not that bad. We've got the cosine difference identity right here, divided by cosine of alpha sine of beta is equivalent to tangent of alpha plus cotangent of beta. So I got to somehow show that these two are equivalent. And I know, like I said, this probably is not something you really like doing, But I do have this formula sheet, and I did post this in D2L. And so let's go ahead and look at the cosine difference formula right here. So I'm going to go ahead and take a little snippet of that to put that in the notes. Let's see my snipping tool. There we go. So take that, paste it. And so I'm going to go ahead and change it out for what I have right here. You know, obviously they're using alpha and beta instead of A and B, but after that, it usually kind of really falls in place. You just have to find these identities, replace it, and they kind of fall in place. So let's see. So this would be cosine of alpha, cosine of beta, and then let's see, plus sine of alpha and sine of beta divided by cosine of alpha sine of beta. Okay, so now what we're going to do here is, see, I have my denominator here. Now, if there was addition or subtraction in the denominator spot, I'd have some issues. But since I have multiplication, I can do this. What I'm going to do is I'm going to break this into two fractions, and then really it's going to come together quite nicely. So let's see, on the first one, we've got cosine of alpha, cosine of beta, and then divided by that common denominator that I'm just splitting this into two fractions, cosine of alpha, sine of beta. Okay, and then plus, and then I got the other half, which is sine of alpha, sine of beta, divided by cosine of alpha, sine of beta. So see, all I did was split this apart. If I were to add this back together, I'd go right back to what I had over here. Now, I don't want to do that, but hopefully you're seeing that these two are equivalent. And then what works out really nice is I had some cancellations. This is going to cancel with this. And right here, I've got sine of beta, cancels with sine of beta right there. And then what you'll notice is cosine of beta divided by sine of beta actually simplifies into cotangent of beta plus, and then sine of alpha over cosine of alpha simplifies into tangent of alpha, and I'm done. So I proved that this that we started with is equivalent to this. Yes, they're in a different order, but that doesn't matter. Addition is commutative. Now, if it was minus, I'd have some issues. I'd have to look back and see something must have went wrong. But addition is commutative, so it doesn't matter that they're in a different order. Okay, let's try another one. This next one, kind of similar to this. I think it's going to be a little bit, there might be little tricks we have to do to kind of complete it, but we've got sine of the difference of two angles divided by sine of the sum of two angles, and then is equivalent to tangent of x minus tangent of y divided by tangent of x plus tangent of y. Now be careful, these are not sum and difference ones with the tangent. Those are just normal tangents being added and subtracted. Over here, I have some formulas for that. So I'm going to go back to my formula sheet, and I've got them right here. So I'll take a little snippet. Paste it. All right. So we're going to do the same thing we did on the other problem. I'm going to replace the difference of angles and the sum of angles with what I have right here. Now this time we're using x's and y's, but anyways. All right, so here we go. So for the first one, let's see, we're going to get sine of x cosine of y minus cosine of x sine of y. Okay. And then in my denominator spot, let's see, I'm going to get, let's see, sine of x cosine of y, but then I get a plus cosine of x sine of y. Okay, so one's addition, one's subtraction. You can't just go crazy and start canceling stuff out. You can't do that. Second, I cannot do the same thing I did up above where I kind of broke it into two fractions. I mean, well, I guess I could, but I don't really see a benefit to that. Okay, so what I want to focus on is, so I've got four parts. You see, I've got four parts. There's one, two, three, and four. And I have one, two, three, and four parts on the other side. So how does each individual part of that turn into tangent, of x or y or whatever? And so this is kind of the tricky part I was telling you about. We're going to introduce something to kind of manipulate this. And so really you just need to focus on one of these. And it really doesn't matter which one you focus on, but we'll just focus on the first one. So right here, how is this going to turn into tangent of x? Well, we know that tangent of x is equivalent to sine of x over cosine of x. Well, I do have the sine of x, but I don't have the cosine of x in the denominator spot. So maybe what I should do is I'm going to multiply everything by 1 over cosine of x. But if I do that to the top, I have to do that to the bottom. So what's going on here is this right here that I've written in purple, that's equivalent to the number 1. That's all that is. So I'm manipulating it because anything divided by itself is 1. So 1 over cosine of x divided by 1 over cosine of x, that's just a glorified 1. It's just kind of, it looks much more complicated than it is, but it's just the number 1. But there's one other thing going on here that I need to take into account, though, because if I do that, I will get sine of x over cosine of x, but the problem is I'll still have a cosine of y. So how do I get rid of cosine of y? Well, I'll just divide it by cosine of y, because remember, anything divided by itself turns into a 1, and so this will just kind of get simplified out of there if I can just go ahead and do that. So I'm going to go ahead and add cosine of y to this also. But remember, what I do to one, I got to do to all of them. So if I divide one of them by cosine of y, I'm going to have to do it to all four of my parts. And so that's essentially what's going to happen here. So once again, this is still, what I have written here is equivalent to just the number 1. That has not changed. 1 over cosine of x cosine of y divided by 1 over cosine of x cosine of y. This is just a 1. But what's going to happen is I'm going to distribute it, and what's going to happen is all these are going to get distributed to all four parts. So all four parts are going to get divided by the same thing right here. So let's go ahead and do that. And then once we do that, it actually works out pretty nice. So let's see the first one. Let's see, we're going to get, oops. We're going to have sine of x cosine of y divided by cosine of x cosine of y. And then let's see, minus, let's see on top, we're going to have cosine of x sine of y divided by cosine of x cosine of y. And then in our denominator spot, let's see, we're going to have sine of x cosine of y divided by what I'm introducing again. Okay. Sorry, this pen is just giving me trouble today. Usually it's not like this. Okay. And then last, let's see, so then plus cosine of x sine of y divided by cosine of y. Okay. All right, so let's kind of see how things shake out here. It should work out pretty nicely. So let's see. Let's just cancel out our common things. So here, 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 and here, and it works out real nice because now everything turns into tangents. So we're gonna be left with tangent of x. Okay, so you can see I wrote this here. The pen is working so slow. I just wanted to write it down and then continue. So you can see that all these right here simplified into tangents. And so you'll also see that it matches what we had at the beginning over here. So I'm done. So I've gone ahead and proved that identity. Okay, I have one left, and looks like we're using a little bit of a combination of the two. So I'm going to go ahead. I need to grab those up here. So I'm going to go ahead and just clone it so I can have it in both spots. Okay, so there's one that I'll need. And then I'll need this other one. Okay, so I went ahead and filled this out with replacing these parts right here with the identities I have here with them. Now, what you'll want to notice is that I'm trying to prove it equal to sine of s divided by sine of t over cosine of t. So what I want you to notice is that this here is the LCD of my two fractions on the left side. And so that kind of clues me in that I need to somehow add this together, the two fractions. But the only way I'm going to be able to do that is by multiplying the left side by cosine of t on top and bottom, and then also multiplying the right side by sine of t on top and bottom. And so I don't have a lot of space, but I'm going to try to kind of fit this in here and kind of show you how this works. So on the right side, I'm multiplying by cosine of t. So I'm just going to go ahead and I got to do it on top and bottom because once again, it's like I'm multiplying by 1. So whenever I do that, what will happen is on bottom, I'll get a cosine of t, which I need. Okay. And then I have to do it on top also. And so I have to do it to both parts of this. So on the first one, it will actually turn this into a cosine of t squared, okay? And then on the second part right here, the minus cosine s sine of t, I don't have one of those, so I got to go ahead and impose it. So I'm going to try to sneak it in here. So let's see, cosine of t. So what I did was multiplied the left side by cosine of t on top and bottom. And so I had to distribute it to both parts on top. And that's why this became cosine of t squared. Then I kind of snuck one in there. And then I put one on bottom. Now I'm going to do the same thing on the right side, but I'm multiplying by sine of t on top and bottom. So this time I'll sneak this one in the front. It doesn't matter. You could put it in the back, but I want my denominators to look consistent. So I'm going to put sine of t here. And I got to multiply that on both parts up here. And I really don't have a lot of space, so I'm going to kind of just sneak it in here. It's going to work. So let's see, sine of t here. And then I already have a sine of t here, so I'm just going to go ahead and square it. So what I did was I multiplied all parts of this by sine of t. Okay, so what I want you to notice next is I'm gonna go ahead and add this together, and I'll go ahead and do it. I'm gonna go ahead and clean it up, and here we go. Okay, so you can see I went ahead and did this. So I added together with the common denominator. So there's the first part, second part, third part, and then the fourth part back here. Now, what you'll notice about this is these actually are going to cancel out because I got cosine of s minus cosine of s, sine of t, cosine of t. Then I have cosine of s plus cosine of s, cosine of t, and sine of t. Now you will notice they are out of order, but that doesn't make a difference. It's commutative. You can move them around if you really wanted to, but you can see I've got this here, cosine of s, sine of t, and then cosine of t, cosine of t. And so one of them is minus and one of them is plus. So I'm going to go ahead and cancel those out. And then I'm going to go ahead and write what we have left. Okay, and so now what I want you to notice here, so I canceled those out, I rewrote this. Now I want you to notice is what they have in common here is they both have a sine of s right here. And so that's a common factor that they have. And so I'm going to go ahead and factor that out real quick. Okay, so that's what I did. I went ahead and factored out the sine of s, and that leaves me with sine of s times cosine of t squared plus sine of t squared. And so that actually is an identity. So let me go ahead and pull up my identities. And it's back up here. It's one of the basic identities. It's one of the Pythagorean ones right here. So if you have sine of some angle squared plus cosine of that same angle squared, it's going to equal 1. And so that's actually what's going to happen here is I can use that right there for this to turn into a 1. So this right here just turns into 1. And then what I'm left with is actually what we were trying to prove. So if you look back up here, sine of s divided by sine of t cosine of t. Sine of s divided by sine of t cosine of t. So I went ahead and validated that identity. So I know they're not easy, but go ahead and practice these, and then you're just going to get a couple of those as your little supplement for exam 1. And if you want further explanation, just send me an email and I'll try to help you out.